Hello there, Mr. Sutton here, bringing you the Pre-Cal Honors 2-7 lesson on applications of polynomials. In this one, we will be finding maximum values for cubic functions, and specifically, the real-life problem, we're going to be figuring out maximum possible volume of a folded-up box. For this lesson, we're going to be using a function on your calculator called fmax. So as a warm-up, follow these instructions, which there's a lot of them. Just pause the video and read them and do them to see if you can do this on your calculator. So here they are. Pause and read. Now that you've had a chance to read all those, I'll show you what I did on my calculator. For my first step, I pressed y equals, and I'm going to enter my function now in y1. Next, we're going to quit out, and I'm going to go to Math 7, fmax. I'm going to go to yvars and call up y1 that I just entered my function into. I'm going to use a comma. I'm always going to type x next. And then I type in the ends of my interval, 0, 12. Press enter. And it's thinking, oh, 4.5 and some change. So next, in order to figure out the y value, this is an x value here that I just found, the x value of the maximum. In order to figure out the y value that's going to give me, I'm going to go back to vars and do y1 again. But this time I'm actually going to plug something into y1. I'm going to plug in the answer I just got, and to get that I can do second and answer down here, and that gives me 1164 and some change. So hopefully you got that. If not, go back and try it again, because you're going to be doing it a whole bunch today. Let's use fmax now to help us with a real-life problem. A manufacturer is cutting squares from the corners of an 8x14 piece of sheet metal, rectangular piece, and then folding the metal to make an open-top box like this one shown below. Now, if you're having trouble visualizing it, here's a GeoGebra website you can go to. So you can pause the video and punch in that URL, or we're going to it now. You can just follow along. So here's the GeoGebra video. So we're starting with a piece of sheet metal. We cut out squares from the corners, and now we're going to fold up what's left into the box. So just looking at where the dimensions are coming from, notice that the length of your squares, or the side of your square, is forming the height of this box here. And then whatever's left over is forming your other dimensions. So let's go ahead now and solve the rest of this. They want a formula for the volume, the domain of the volume, so the x values that you're allowed to plug in, and then the maximum volume. And just as a starting point, x is the side length of one of these cutout squares. So let's label this diagram below here. We know that x is our height. And then this length here, we started with 8 centimeters, but we cut 2 squares out of it, and those squares each had a side length of x. So that's 8 minus 2x down there. Next, we have 14 centimeters for this side, except that we're losing 2x from there as well. One of those x's for each of those squares. So that's 14 minus 2x there. Now for volume, we know the volume of a rectangular prism is going to be length times width times height. The length we said was 8 minus 2x. The height was 14 minus 2x, or the width was, and then we have a height of x. Next, they wanted us to find the domain for this. So in terms of acceptable x values, one thing we're going to do to find domain here is we're going to find all the zeros of this functions, and I'll explain why we're doing this in just a sec. But finding the zeros of this functions, we've got 4, 7, these are the things that zero it out, and 0. So for a real-life problem, the domain is all the values that it makes sense to plug in a real-life situation. So what is x exactly in real life? X is the height of these squares. X is the height of your box. What's the smallest x can be? Well, I mean, we can't really get smaller than 0, right? If we have a height of 0, then we don't really have a box. Now, what's the biggest x can be? As x gets bigger and bigger, you're cutting into these other dimensions of your rectangular prism. Right here, if x becomes 4, you'll have used up this whole length side here. Now, if x becomes 7, you'll use up this whole width side, but you're going to use up the length before you use up the width. So the highest value you can have for x is a little bit less than 4. Otherwise, you, again, don't have a box. So our domain then, this is where the dimensions run out. Our domain is going to be everything between 0 and 4. Now, you might wonder why we bothered making you find the domain. Why not just find the maximum? Well, in order to find the maximum, you might have noticed on that opener problem that fmax requires you to enter a lower and an upper bound. Where do you think those are coming from? The domain, right? We don't want to look outside of the domain because then whatever answer we get might not be realistic. Also, a little bit more kind of theory side of this. When you're looking for the maximum of a function, I mean, you're looking for the highest point, but this is a cubic function right here. This is x to the third power. Now, you might remember from the graphing section we just did that cubic functions go up forever as you move to the left or the right, depending on whether it's a negative or a positive. If you've got a function that goes up forever on one of the sides, are you ever going to find a maximum if you look at the entire function? Of course not, because you can always go a little higher. So we have to set limits in order to actually find a maximum. So let's go ahead now and plug this into fmax. You do it on your calculator, I'll do it on mine. So here I've entered my function into y1. Now I'm going to use fmax. And again, 0 and 4 are going to be my lower and upper bounds using fmax. And that gives me, survey says, 1.64-ish. So that's my answer for this one. This is a real-life problem, though, so we should also have units on this. So that's 1.64 centimeters, they said. And then we're going to plug that back in, because this is the x value now. This isn't the actual volume. This is the length of the square, the height. We'll plug that back into y1 to get our volume. So plugging this answer into y1 gives us, they said, 82.98. So that's going to be 82.98. Now the units on this, since it's volume, is going to be centimeters cubed. Let's do another one of these examples. Pause the video, read the problem. It's pretty similar to the last one, except I didn't give you a diagram. Feel free to draw your own, and then see if you can solve the whole thing. All right, now that you've gotten a chance to tackle this on your own, here's our diagram, the cutout squares rectangle diagram. You'll be drawing this one a lot. We got an x here. This will be 15 minus 2x, or you could make that this side. It doesn't really matter. If this is 15 minus 2x, then we've got the other side was 12 feet minus the 2x squares that we took out. Volume, we've got 15 minus 2x times 12 minus 2x times our height of x. Now we find our zeros for this. That's going to be 7.5, 6, and 0. Domain is going to be from 0 to the smaller of these two values, because it's at the smaller value, that's the first side that we're running out of. That's going to be this side here. If you plug in 6, you run out of this width side. So from 0 to 6 is our domain. Those will be our numbers that we enter into our grapher under fmax. Let's go ahead and do that now. So here's my function entered into y1. And if you've done a bunch of these in a row, I kind of just leave the parentheses here and plug in different numbers. It's usually minus 2x. Going back to the main screen and doing fmax, now we're going from 0 to 6 on that function. Comes out to 2.21. And then let's go ahead and plug that answer back into the function itself to find the volume, which is 177.23. So that's 2.21 feet and 177.23 cubic feet. So that's it for this one. Hopefully you've maximized your understanding for this one. Until next time, Mr. Sutton signing off.